Hello everybody, this is our lecture number 7, and today we're going to talk about K-maps or Karnaugh maps. That's a technique for simplifying Boolean equations. So we used Boolean algebra to simplify equations, but it's really prone to errors because it requires you to memorize some rules, memorize theorems. So Karnaugh maps are a graphical method for the same task. It was invented in 1953 by Maurice Karnaugh. And as we know, logical minimization involves combining terms. So, for example, we have here that we know that we have two implicants here. So P, A, and or P and complement of A. And we know that we can group those two implicants together to eliminate the variable A. So we know that if we have complementary forms here, like A and complement of A, we can eliminate this term here, and we group these two implicants just with the meaning of P. And the idea here is going to be that we can represent the truth table in a two-dimensional grid for 2, 3, or 4 variables. And there are also 5 and 6 variables K-maps, but we're not going to be covered in this course. So the idea is that the same representation that I have in a truth table, I can represent in this grid, for example, for A and B, where this row represents complement of A, and this represents A, and in this one is where the term B is complemented, and this is where B is not complemented. And we can see that this square here is this term, so complement of A and complement of B is 0 for this function. On this term here, complement of A and B, it's also 0. A and complement of B, it's 0. And if I have A and B, is this term here is true. So this function is only true if I have A and B. So that's the idea. You have one side of the grid for one variable, the other side for another variable, and and the square is going to represent the terms where they represent the terms of your equation. For example, we have or here, A or B, and we know that it's where A or B is true, the function is true. So 0 and 0 is going to be 0. Complement of A and B, so 0 and 1 is going to be true, 1 and 0 is going to be true, and 1 and 1 is going to be true. And for example, an exclusive OR, that we have one of them are true, but not both. So if it's 0, it's 0. If both are 0, it's 0. If B is true, so we have A is false and B is true, it's true. If A is true and B is false, it's also true. But if both are true, it's 0. So you can represent the same. You need to. It's just another representation of a truth table, where the mean terms or the terms are shown as the implicants. So we're also gonna use the term implicant because this term here, A and B, implies that this function is true. So this is an implicant of this function. So it's another one that's a little bigger. So we have this function, and we remember that we have the representation of sums of products here. So that's gonna show us how to represent on a Karnaugh map as well. For example, we have complement of A, B, and C for this function is true. So we can see that the complement of A, B, and C is this square here. And the idea of the Karnaugh maps is that we need to put the closest mean terms together. So that means that we're not gonna we're trying to avoid, we're not gonna accept where both digits change. So we want the digits to change in the smallest possible. So we have 0 and 0, so B, it's complement of B, complement of C, it's complement of B and C. And here we jump for 1 and 1 because only B changes. So that's the idea. So we have the two implicants that only changes in B, it's together, and here only the two implicants that the changes C is together. So this is gonna help us to simplify the equations, because all the implicants, they are similar, or they are close together. They only change one variable, they are close together, and that's what enables us to use this form to simplify. I'm gonna repeat again. So we have only from these terms to these terms, so this column to this column, only B changes. B, it's complemented here, and here B is not complemented. It's just B, and this is just one change between these two and these two as well. What gives us a little weird table, but it's the only way that we have for simplifying. So when we count the squares, we're gonna count 0, 1, 3, and 2, because this is because we need the only B changing, so we have the number 3, quote unquote the number 3 here, and here we have the number 2. So yeah, the idea is that only one digit changes, so we can group them together, because only one variable is changed. So in a similar way, we're gonna have the 4 variable K-map, and we can see that again we need these implicants here, the rows, to change only one variable. So we have A and B in this case, and they only change 0 and 1, and here only A changes. So from this line to this line, B keeps the same, it's true, and A changes from 0 to 1. So again, if we're gonna count the numbers here of the midterms, it's gonna be 0, 1, 3, 2, 4, 5, 7, and 6. And here, instead of going to 8, we're gonna switch, and this row here, if you count, it's gonna be 12, 13, 15, and 14. We're gonna see that in a bit with the numbers of the midterms, but it's just because, so keep in mind that we switch these two columns and we have to switch these two rows as well, so we keep the similar, we only change one variable at a time on the whole table. So yeah, so Karnaugh maps for simplification, I think you can see that this expression here, A, B, it's defined here. So we have A and B, it's true, and A and complement of B is true. So if you translate that to a Karnaugh map, would be, here is the complement of A, and A, complement of B, the column, and second column is B. So we have A and complement of B, it's true, and when I have A and B is true, and we have two implicants here, and we can have a bigger implicant. We can group these two implicants together, and you can see that the only changes, the only change that we have, it's on B. So if you group these two implicants, B changes. So it's not I cannot use B because it's changing on the same implicant, and only A, it's kept here on the same. So we can group this together, and the result is going to be that this implicant means A, only A. So that's the simplification of this truth table here. So we have the truth table. We see that they have two implicants here, and I'm gonna have one that's called prime implicant, that you can group together those two implicants and have a simpler version of the equation. So in a little more complex, so that is the same equation that we had before with 3. So you can see that I have here A complement of B and C. It's going to be this guy here. Here I have complement of A, B, and C. So complement of A, B, and C, they are both true. Here I have A, B, and C. So all three are true. And I have here A, B, and complement of C. So A, B, and complement of C. So this Karnaugh map describes this equation. And we can see that I can group together some of them here, right? So this is a prime implicant. This is a prime implicant, and this is a prime implicant, as we show here. So in the end of the day, I have these two here. So I have this. Let's go back here. So we have these two here, and I can see that the only variable that changes is C. So C here is 1, and C here is 0. So when I group these two together, it's A and B, because they are the only two variables that are not changing. So in this case, it's A, and you can see that on these two rows, B doesn't change. So it's A and B. So you can see that the first implicant here, the first term, it's A and B. And we can group the rest as well. So we have this guy here too. We can group together another one. So it's A, and you can see that B changes this time. So we have C that keeps the same variable, and B changes. So we don't use B on this one. We can eliminate B, and we have A and C. And we can group in the vertical too. So the vertical here, you can see that A changes. So we're not it's complement of A first row and the A in the second row. So you can eliminate this, and B and C doesn't change. So we have B and C here. And it's I think it's pretty clear that we can group powers of 2 implicants. So we can group 2, 4, 8, or 16 implicants. So here again we have the behavior of NAND. That's the opposite of the AND gate. So the truth table is going to be like this. We have those 3 implicants that are true, and when you group them together, we can group this one here. That's going to be a complement of A, or complement of A and complement of B, or the complement of B. And that's basically what's happening here, right? Is the NAND gate. So just a little term summary. So an implicant is a Boolean function term that makes the function true. So in this case here we can have the min term, or the term of the sum of products. But we also can have a Karnaugh map that uses max terms. So a max term is also but in this case you're gonna use this prime implicant, and your representation is gonna be the opposite. So a prime implicant, it's a variable that cannot be removed. So it's the representation of the function. It's any group of squares or rectangles. So when we group here, this is a prime implicant. This is an implicant, all of them, but this is a prime implicant. This has to be in the final equation to be true. And in an essential prime implicant contains a min term that's not covered by any other prime implicant, by any other implicant. So a prime implicant, for example, this guy, it's a prime implicant. It's not covered by any other term, and this one as well, it's a prime implicant. It's essential prime implicant. Sorry. So yeah, so you can see that we can describe the min terms of truth table in the Karnaugh map, and it's always if you use A, B, and C. I've seen on the textbook you can see that C, B, and A. It's okay. You just have to change the order that you have your min terms. And if you look the labels of the rows and the columns, it's going to be pretty easy to see how to organize your min terms here. Usually what I do, I use A, B, and C. So I start from the left. So if it's for like this, I use A, B, C, and D, the same way that we have here. But some people use the opposite way. It's okay if you write your Karnaugh maps. If you place the min terms in the correct place, it's gonna work the same way. So okay, so in this case, when you organize this way, you have min term 0 here. That's the first one. So 0, 0, and 0. So 0, 0, and 0 is this guy here. If the min term 1, 0, 0, 1, and 1 come here, and that's where we only want one variable to change. So only B is gonna change. So we have min term 3, that's this guy here. So it's 0, 1, and 1. So min term 3 comes to this spot, and min term 2 goes to this one. And when you go to the next line, we have min term 4, 1, 0, 0, this guy here, and min term 5 again. And we have to switch these two as well, because these two columns are switched. So the min term 7, that's 1, 1, and 1, the last one here, it's this min term here. It fits, we place on this square here, and min term 6 goes to this. So these two columns are switched. So we have 0, 1, 2, 0, 1, 3, 2, 4, 5, 7, 6. That's how you organize these min terms. We're using A, B, and C. So in a 4 variable K-map, it's gonna be almost the same, but we have to switch these two lines as well, because we want only A in this case to change between these two lines. So the min terms will be as the same before, 0, 1, 3, 2, 4, 5, 7, 6. But this line, it's going up, so it's 12, 13, and remember that we have to switch the column, so it's 15 and 14. And the last line is 8, 9, and we have to switch the columns 11, 10. So this is how we organize the min terms of a truth table of 4 variables. So I will provide an extra, as the same as I did with the Boolean algebra. I will provide an extra video. This class is not as long as the other one, but I think it's better to split this type of videos. So I will have an extra video using K-maps or Karnaugh maps for simplification. I'll have some examples of simplification using K-maps. Okay, thank you everybody, see you soon.